Hello, it's that time again. It's time for question number 4 on the worksheet. So in this one, basically what we're doing is we are pruning a binary search tree based off a minimum and a maximum. So if you've just done the previous problem, you'll notice immediately that there are some similarities here, right? In the previous problem, we were saying, yes, this is a BST, or no, it's not a BST, based off some kind of bounds. We were establishing a minimum and a maximum for every node that we could have. We're going to do something very similar here to help prune our BST. So I'd recommend you do problem 3 if you have not done that before looking at this problem. Anyway, just to explain a little bit more detail, what's actually going on here is we are going to be given a BST. Let's take an example. Let's say it's 5, 3, 2, 6, 7, something maybe looks like this. And we're going to be given an L and an R. L basically functions as our min, R functions as our max. So let's say that our L in this case is going to be 3 and our R is going to be 6. Basically what we want to do is we want to only keep the nodes in our BST that are strictly inclusively between these two numbers. So anything that is 3 or greater and 6 or less. In other words, if we feed this tree into this print_bst function, we want it to end up looking like this basically, where we've made the left child of 3 null and the right child of 6 null, because those numbers are outside of our left and right bounds, and we're left with only the numbers that are strictly inside. Okay, so a little spoiler here, whatever. Anyway, so that's basically what we have. Another thing to notice here, just a minor thing, is that I think this problem is from maybe a different past exam or something than the previous problem. So notice that we are calling the value inside of our node label this time instead of val. And we're calling this root instead of t. It's called BST instead of tree node, like whatever. It's the same thing, just different names for it, basically. Okay, so every BST has left and right child, and if it's null, there's no left or right child. Okay, the first thing to notice about this question is it's actually much trickier than you might think it would be. So perhaps when you saw me do that, when you figure out how to do this, your first thought is, okay, this isn't that bad, because right, all you have to do, you might think, is go down to L, go down to 3, or whatever number is closest to 3, the first number that is greater to 3 that is not 3, basically. And then you just set the left child of 3 to be equal to null. And then you go down to, say, 6 and set the left child of 6, or the right child of 6 to be equal to null. And you might also think, okay, well, if we have a case where something like this, right, where the left is 3, we would cross this out, and then the right is 6. Notice there's no 6 in the tree. So you basically go to the greatest number that does not exceed 6, which in this case would be 5, and you just set its entire right side to be null. You might think that's all we have to do, but it's not that simple, actually. And here is an example where things are not so simple. So let's say that we had a tree that looks something more like this. Okay, so take a look at this tree. It's a little bit more complicated, but it holds all the binary search tree properties, right? Everything to the left of 6 is less than 6. Everything to the right is greater than 6. What's going to give us a bit of an issue here is this 3 here. So let's try to think of that strategy that we just did before and see what's going to happen. Okay, so we want to have this idea that we want everything that is less than 3 to be cut, and we want everything that is greater than 3 or greater than 7 to be cut. So that's going to be this 8 and this 2. Notice there's a problem here, because if we were to, for example, just basically go to 4 and say, okay, the left child of 4 is now null, that doesn't actually work, because even though 2, the thing that is immediately to the left of 4, is less than L and therefore should be cut, something beyond 2, right, something to the right of 2, this 3 in this case, should not be cut, right? So in reality, we don't want to just strictly say, the left of child of 4 is equal to null. We want to cut this node, and we want to cut this node, but we want to end up having 3 here, right? In other words, we kind of want to skip over this 2, get rid of this 2, and move the 3 up to be the left child of 4, right? Okay, that's going to make things a little bit trickier here, and that's the main kind of edge case to look out for in this problem. Okay. So now that we've kind of understood that if we can do it on this tree, we can probably do it on any tree. Now we can start looking at the code a little bit more and maybe even consider some simpler cases before we get onto the more complex cases. So keep this in the back of your mind for now, because we'll need to address it eventually. But let's start with a really, really simple case. So let's start with something that looks like this: 6, 5, like this, and we want to cut from 6 to 6. In other words, we just want to end up with this. We want to end up cutting the 5 node and only having the 6 node in our tree when we prune. Okay, how are we going to do that? Again, you'll notice that this starter code looks pretty similar to the previous problem because again, it's just a recursive function where we have a base case, we have some kind of if conditional and setting stuff, and then we have recursive calls, basically. So let's fill out the kind of easy things first, the things that we can just kind of copy and paste from other places. So the first thing is going to be if the root is equal to null, we're just going to return null. This problem tells us to return the root of the tree at the end, so we're going to return the root at the end. And those are the easy things. Okay, so now let's think a little bit about how this is going to work. So again, if you remember from the previous problem, from problem 3, remember that when we were deciding which nodes, when we were looking at different nodes, right, and we were assigning bounds to different nodes, we weren't looking at the children, we were looking at the node itself, right? We weren't saying, hey, is my left node less than me? We were saying, no, I am this node, am I less than my parent, right? We were making reference to these bounds from like ourselves rather than looking at our children. Here we're going to do something really, really similar. It prevents us from doing null checks and it's going to make things cleaner. So in general, what we want to do is we basically want to say, am I a valid node, right, for a given node? And if I am, then I stay as I am. And if I'm not, then we're going to replace me with something else. Okay, so in other words, basically what we're going to want to do is we're going to want to start at 6, recurse to 5. We're going to see 5 is not in bounds. And then what we're going to do is we're going to set root.left, right? The left set child of 6 to be null. And that's how we're going to get rid of 5. Okay, so all that logic in place, maybe we can start to figure out that this is going to be setting root.left. And this is going to be setting root.right. Right? So notice here that the recursive calls are not just being returned as they were in the previous function, they're actually setting something, right? And why are they setting something? They're setting something because that's exactly what we're doing, right? We know that, for example, in this tree again back up here, we know we're going to have to change the left child of this 4 node, right? Okay, so let's look at this one more time just with this logic. Basically what's going to happen is we're going to start by passing in 6. 6 is not null. Then we're basically going to check if 6 is in bounds with these things. 6 is going to be in bounds in this case because it's, you know, both greater than or equal to and less than or equal to 6. Then we're going to move on to setting its children. So we're going to say root.left, which is this one, is going to be equal to a call to the left node, right? So we can fill this in too. This is going to be root.left. The bounds are not going to change each time, so this is just going to be LNR still. And now let's think, well, now we're on the 5 node. We're going to say, is this root? We're going to say, is it null? It's not null. So we're going to check, is it in bounds here somehow? It's not in bounds. So in this case, we probably want to return null, right? And once we return null, where are we returning null to? Well, we called that from this prune BST method in the first call before we recursed. So this is going to return null. It's going to set the root to be null. We're going to be done. That's basically how this is generally going. And we were able to fill out this along the way. Another thing to notice is that pretty much everything we do to the left, we're just going to mirror on the right. So we're going to have something like this. Notice also all these prune BST calls, they're just passing in left and right because left and right never change, unlike in the previous function we did where they represent ever-changing bounds for every node, because every node has different bounds. Now we're just checking one general bound, so you can kind of fill that in everywhere. Okay, so the next big thing we need to figure out is what are these conditions? So these conditions are the conditions that check if a given node is in bounds. So once we know that, we can start figuring out, we just say if root.label or root.val, whatever you want to call it, is less than L, meaning that we are not in bounds. In the example up here to my right, that would be, for example, 2 would hit this if condition. We don't just want to check null. So here's the next big thing. So again, remember, we have this weird condition here where we want to get rid of 2, but we don't want to get rid of 3. If it was a simple case where you didn't have to worry about this, like the case I just did, we could just say return null right here at this line. But keep in mind, we don't want to say return null here, because if we say, okay, well, if the root is less than null, return 2, what's going to end up happening is when we call this line, when we're evaluating 4, it's going to recurse down, it's going to return null, And then we're going to set root.left of this node to be null, which would cross all this out. And of course, we don't want to get rid of that 3, right? So what we want to do instead is we want to return another call to prune BST. And what do we want to prune? We want to prune the right side of 2. Why do we want to prune the right side of 2? Because remember, the right side of 2 could have an element that is within bounds, which is the case in this example, right? We don't need to look at the left side because we know if our root is less than L, then nothing to the left is going to be greater than that. So there's no way that anything to the left could be of value to us, but there might be something to the right too that will be of value to us. So that's why we're going to do that. And which means we're going to return root.right right here. Okay, so again, in summary, we know at this point, if this condition is tripped, we know that the node we're looking at is too small to be included in our tree and needs to be pruned. However, it is possible that to the right of that, there is something that is big enough, right, that does not need to be pruned. So rather than just returning null right there, we need to return another call to prune BST. Okay, and then following the logic through a little bit more, hopefully you can see that when we are evaluating this for node, we're going to call this case, we're going to say, we're going to try to reassign root.left. We're going to reassign it to be pruning whatever the left subtree is, which in this case is 2. When the left subtree is going through this function, it's going to trip this condition, and then it is going to return its right subtree that gets pruned. Its right subtree is not going to get pruned, it's just going to return 3. So this is going to return the 3 node. And remember, what was this function returning? The one that we called on the left node originally, it was returning to root.left. So in other words, we return root.left on prune BST and pass in the 2 node, and it's going to return the 3 node to us. In other words, it's basically going to skip over that node. And so we're going to end up with something like this. We're going to say this line right here equals the return of calling prune on the 2 node, which is the 3 node. So it's just going to point directly to the 3 node, and then this is going to get erased. It's going to get garbage collected. So we're going to end up with this. Everything else, this part is the same exact thing, except it is mirrored. So it is just root.label is greater than R, and it's going to return root.left LNR. And that's just because a mirrored thing could happen on the same side, right? You could end up in a situation where, for example, you know, you have like 7 point, or actually this example isn't really set up very well to do it, but basically you can imagine an example where you go right and you say, hey, this node is not valid, but there's something to the left of this node that is valid, and you do want to include that. It's just mirrored in the same way. Okay, so this is how you would do this question, how you would address it. I hope this makes a little sense. Again, this is a very hard question. There's, you know, I think it's very hard to even come up with this particular case we just did, this edge case. It's very easy to just think, oh, you just need to set things equal to null. Not quite correct in this case, but I hope this makes some sense.